Welcome back. Let's continue the discussion on Rankine-Huguenot relation. So, we'll finish this particular one which we are discussing right now on deflagration wave and detonation wave. So, the deflagration wave we have done the analysis for a simple system, and now we are in the middle of the detonation wave. Okay, so this is where we actually stopped. Actually, this started with a particular system like this, and we had an upstream condition, we have some downstream condition, and these are the set of assumption that we had, something like 1D steady, tube area is constant, ideal gas assumption, constant and equal specific heat, adiabatic conditions. So, all these are taken into, and obviously no body forces which are considered. So, these are considering these assumption, we have looked at our mass conservation, momentum conservation, energy, then using the expression for enthalpy, we finally got this for the Rayleigh 9, where with a different mass flow rate we get this, and then finally we got the from the energy, mass and momentum when you combine, and also when you write gamma equals to the ratio of the constant pressure specific heat to constant volume specific heat, this is what we get. Now, where Q is the known parameter. Now, we will further we will fix now P 1 and 1 by rho 1. So, once we do that, now this equation 11 becomes transcendental relation between P 2 and 1 by rho 2, or rather in generically one can write that P and 1 by rho, that becomes 0. Now, one can plot this pressure versus 1 by rho for, let us say, P 1, 1 by rho 1 and Q to be fixed at particular known values, and the point or the coordinate of, let us say, P 1 by rho 1, this is essentially known as the origin of the Rankine-Huguenot curve. So, what one can see that, or rather note that the RH curve does not pass through the so called origin. So, RH curve does not pass through so called origin, which is essentially the intersection of x and y. Now, we can plot this pressure versus. So, this axis it would be pressure, this is 1 by rho, this is pressure. Now, we can have a curve like this, where this is one point, and we can draw a tangent to that point. Then this will cut through, then this will also cut through a point like this, and this will also pass through the tangent of this point. So we can have a curve which is going through like this. So this point you say, let us say you start some point, this is D, this point is B, this is a point which you call C, then there is, this is the tangent, let us say E, and this is a point which pass through called A, and this is your P1 and this is 1 by rho 1, and this particular curve is your Huguenot for P1 1 by rho 1, and this dotted line are all Rayleigh lines. So this is what you get. Now the point is that question which may arise, what point this Huguenot curve correspond to a realizable physical state. Now one can see any real process which pass going through the point 1 and 2 must satisfy this Rayleigh and Huguenot relation. So there are few limiting situations. This is above D, this is a situation where you have strong detonations. D to B, this is weak detonation. C to E, weak deflagration, and below E this is strong deflagration. So these are the sort of different, one is above this point, then one segment is D to B, another segment B to C or C to E, then below E. Now we can define our detonation velocity. So the detonation velocity you can define at Vd. Okay. So this should be equal to the V1, which is essentially velocity at which the unburned mixture enters the detonation wave. Now if you recall from that particular figure, you have these, then all this state 1 and this is state 2. Now detonation for state 2 will be the upper Cj point at which is velocity is sonic. So then we can write rho 1 V1 equals to rho 2 C2, where your C2 is gamma R2 T2 is the sonic velocity. So then one can write V1 equals to rho 2 by rho 1 gamma R T2. This is our equation 13. Now we try to relate this with the density ratio rho 2 by rho 1 and T2 to state 1 or any other available known quantities. So then what we can write, that we can write from our momentum equation, this equation, equation number 2. So that equation we divide that momentum conservation by rho 2 V2 square and neglecting P1, as compared to P2, we get rho 1 V1 square by rho 2 V2 square minus P2 by equals to 1. 14. Now we apply the continuity equation. Continuity, that is equation number 1 into 14. What we get? Rho 2 by rho 1 equals to 1 plus P2 by rho 2 V2 square. Now we can replace V2 with C2. So this will become rho 2 1 plus P2 by rho 2 gamma R2 T2. Now we use some ideal gas law, that is P2 equals to rho 2 R2 T2, which will get us rho 2 by rho 1 equals to gamma plus 1 by gamma. So that's our equation number 17. Now once we solve the energy conservation equation, so if we solve the energy conservation equation for T2, what we get? T2 equals to T1 plus V1 square plus Q by Cp. Again here, if we eliminate, now we can eliminate V1 using continuity equation, and also using C2 equals to V2. So what we get for T2 equals to T1 plus Q by Cp gamma R2 T2 by 2 Cp gamma plus 1 by square minus 1. So this is what we get. Now we can use another relationship, that is gamma minus 1 equals to R gamma R2 by Cp. If you use this, the above solution turns out to be gamma square by gamma Q by Cp. Now we use this one and the previously obtained equation. So if we use equation 20 and this one 17 and 17 into relationship of V1, that is in 13 into equation 13. So that's get me Vd equals to V1 equals to 2 gamma plus 1 gamma R2 T2 Q by Cp to the power half. So if you look at this particular equation, is an approximation or approximate equation, because of all simplified assumption employed, and also one of the critical assumption that we have used is P2 is much higher than P1. So this particular one is a simple equation or rather approximate equation. Now if we little bit relax the assumption of, let us say, constant and equal specific heat, we get more accurate but still very approximate equation. So if we relaxing Cp equals to constant assumption, So, we get slightly more involved or complicated system. So, which will get us to gamma 2 square by gamma 2 1 plus Cp 1 by Cp 2. So, it will involve different Cp 1 and Cp 2, which will get Vd equals to 2 gamma 2 plus 1 and rho 2 by rho 1 equals to by gamma 2. So, that will have a different these things, but still these are all approximate expression. Now, if we go back to this particular curve and look at this, we can comment on these things, like let us say we take a segment which is above D. So, characteristics is that strong detonation. So, you can say segment characteristics, burned gas velocity, and some remarks. It is subsonic. So, we can put some category like this. This is seldom observed. Special experimental equipment, you need special experimental equipment to get that particular state. Now, second is we can have at point D, which is upper Cj point, which is sonic. So, this is observed in tubes. Now, the segment DB, which is weak detonation, here speed is supersonic. This is also seldom observed. BC, this is sort of inaccessible location. CE, we get weak deflagration, speed it subsonic. This is often observed, pressure is order of 1. Point E, this is lower Cj point, sonic, this is not observed. And finally, below E, strong deflagration. So, this is supersonic. This is also not observed. So, essentially if you categorize that whole curve, that Huguenot curve, there are different zone, and if we just go back to that curve to conclude what we said, some points which is above D, you will get strong detonation wave and the burn gas velocity would be subsonic, but this is not a situation which is often observed. This particular point, this is upper Cj point, and this is your sonic speed, will be the burn gas velocity would be sonic, and this is observed in tubes. This is your weak detonation dB. Here the gas velocity, unburned gas burn gas velocity would be supersonic. This is also not often observed. B, C, these positions are not accessible at all. C, E, which is again weak deflagration wave, which is often observed in the system, and the burn gas velocity is subsonic. And point E, this is a lower Cj point, so not observed sonic velocity, and below this point this is strong deflagration wave which is supersonic and not observed. So, this is what we have summed up in this table. So, that is pretty much what we wanted to talk about this Rankine-Huguenot relations. Now, that covers all your essential basics for what you think about basic combustion characteristics, thermodynamics and all this. Now, we will move to turbulence, and there onwards our actually the all discussion would be talking about the turbulent and turbulent reacting system. And to continue our discussion in this, we need to have those basics, especially when we talk about how turbulence interact with the reacting flame front. We will see the information of our basic understanding of the combustion, and those will come. So, first we will touch upon the turbulence, and this is what we would go about it. We will first see what turbulence is, because this is a very important topic of interest, and this is one of the classical still not well understood problem in physics or nature. So, we will see how we try to characterize it, how do the flows behave, because these are important, because once we understand the characteristics of the turbulence flows, then only we can understand how turbulent and reacting flows would behave. So, right now you may assume what we are heading up to. Basically, we are going to discuss on turbulent reacting system, where the importance aspect of it is the turbulence and turbulent flows, because now once you have what we have done so far is the all these reacting system under laminar condition. So, the underlying flow physics or the fluid mechanics is quite nicely behaved, but once you come to turbulence, we can see how the behavior is, and depending on that behavior we need to look at how that flow behaves. Now, then we have to, once we understand how the behavior of the flow field, we need to characterize it. So, essentially we have to describe it not only qualitatively, also quantitatively. So, that means essentially we need to characterize the flow field quantitatively, which is very important, because this quantification has a direct impact on the reacting system. So, these quantifications are quite important, not only qualitatively, it is quantitatively. Then we will look at what are the fundamental physical processes which are involved, and then finally we will, once we are done with this theoretical part of it, we will see the modeling part of it and how things are simulated in the modeling perspective, because this is one of the important these things. So, this is how one can look at it. It is a simple flow around a sphere, and this diagram is well known, a diagram if you have done advanced fluid mechanics or something. So, when the flow past a sphere at a high Reynolds number, so the Reynolds number is one of the parameter that we will use upstream velocity, characteristics length divided by kinematic viscosity of the flow. So, this Reynolds number is quite important to see the characteristics of the flow, whether that is laminar or turbulent, and RE 15,000 is absolutely a turbulent flow field, and if you look at the images, this is how it looks like. There is a lot of, I mean, this portion, if you see it specifically, you can see the randomness in the fluid motion. These are smoke visualization, so which clearly shows the randomness in the motion of the flow field. Now, compared to that, if you come to R equals to 8.15, if you see this, the flow looks nicely behaved. That means it comes along the sphere, go along with the sphere, along with the stagnation point, and there is a well known friction curve versus the Reynolds number for the sphere, which goes like this or scales like this, then there is a, then it comes down and then there is a drop. So, this portion which follows the Stokes law asymptote, that is friction factor is 24 by. So, this portion which is a linear curve which follow 24 by RE. Now, at this point the Reynolds number is laminar, and there is a, from here to here, this follows a curve which is f equals to root over 24 by RE plus some constant to the power square. So, it is an parabolic curve which follows here up to Reynolds number 6 into 10 to the power 3. Then at this position this becomes completely turbulent, and you can see the friction factor that remains quite flat for some time, and this is a sudden drop in the friction factor, and the drag force which is basically expressed by the fear, it would be pi r square. V infinity is the upstream velocity and the function of the RE. So, this friction drop in the friction factor is quite important. Here you start feeling some drag crisis, which is often known as a drag crisis. So, there is a similarity of this particular sphere problem with an, if you are a cricket lover, there is a nice similarity between the cricket ball, and we will discuss as we go along with the discussion of this. So, we will stop here and continue the discussion in the next lecture.